This is when aspen established naturally from seed, it is very important where that seed lands. So there's a reason why an aspen tree produces millions of seeds, because it's a random chance of a seed landing in a certain spot. So the more seeds you have, and if they don't cost you much, you can grow 1 million of them, they land everywhere, and then somewhere it's some good stuff where they could grow. And what we found is that microtopographical position plays a huge role. If we look at where a seedling established, a 1-year-old seedling, what we found is a much higher proportion of seedlings established in concave microsites. These are little, just very small. Our microsite was not much bigger than this in diameter, so if you had a little divot, that already was enough for a seed potentially have a higher probability to establish. Okay? While flat, convex, and slope did not do as well. Okay? You get seedlings on there, but not as many. The other thing what we found is very important what type of substrate they land on. If they land on pure peat, not much is going to happen. This pie chart gives you about an idea. Deep organic matter is pretty much like peat. You have, I don't know what it is, a tiny slice. Most of our aspen seeds establish on mineral soils. Okay? They need that moisture of that mineral soil, I guess, and the finer textured material and the nutrients likely coming out of that in order to establish properly. However, mineral soil is not the same as the next mineral soil. If you look at the natural soil, what we did is we looked at the organic material, then we looked at the gray is the AH horizon, and we have some sort of a BM and then a BT. So we just split the soils and we grew the seeds on these different soil horizons, and as you can see, there's a very big difference in how it expresses on the seedling. What you get is very different depending on what the substrate is like. So the top is an AH horizon, then you have the BM and your BT, and on the left side is aspen, on the right side is balsam poplar. You can see balsam poplar doesn't really care. We see balsam poplar a lot more on reclamation sites than we do aspen, for example, as seedlings. Okay? So that was an experiment in which we finished about 2 years ago, where we had different substrates from the Aurora mine out at Synkrut, and we had B horizons, peat mineral mix of forest floors, and all kinds of different. And here you can see the productivity of the aspen, how much it can vary just by what soil we get, okay, what substrate we have. Now, reclamation site, and I think George didn't make it. This is out at Genesee at the coal mine. You can see it on top there in the right corner a bit. We had a reclamation site there, and reality is our operators are trying to do a good job. And they're doing a too good a job, because generally what we create is parking lots. And the parking lots have no microtopography. So if we want to create these conditions for actually natural seeds which are free to land and to actually grow, that is, if we don't create the microhabitat for them, they will not grow. They will land there, but they will never become seedlings for us. So we did a study on microsites there and where they grow. Now, I talked about seedling quality. This is kind of the type of stuff I got initially. These are little aspen seedlings. They barely grew any leaves, or their root systems were very poor, or they had really poor qualities. They grew as shrubs more than as trees. Okay? So that was really something I wanted to look at. This is on the right side is a natural aspen seedling grown from seed, just seeded and established. Looks quite good. And this one is a 2-year-old aspen seedling planted on a reclamation site. So that one grew about 2 centimeters. This one grew about 20 centimeters. Of course, soils play a role, but also the seedling quality does. So what we did is we tried to learn from that experiment I told you before, where the aspen seedlings grew big root systems, lots of reserves in that root system and so on. And these are all the same seeds. So the seed source is the same, and you can see the variation of seedling size and habit. They look all a bit different. These are, I think, 12 different treatments, and they all were a little bit different. And so we were able to grow root-shoot ratios pretty much from 1 all the way to, I think, 10 and root carbohydrate contents, which are the reserves, from pretty much 10% all the way to 40%, which is pretty much represents a potato. Okay, there's a lot of starch in there. And what we found, once we planted out these seedlings, what we found is a beautiful relationship with root carbohydrate reserves and how they performed in the field. This is a very nice, so you can pretty much double your height increment in 1 year by just putting out better seedlings. That's what it boils down to. Also what we found is, and I want to point out only the bottom right graph, is that the seedlings with a high root-shoot ratio, meaning also high carbohydrate content, reserve content, these are the gray bars on the bottom right, outperformed, that was at, I think it was at Suncor or at Syncrude on a reclamation site, outperformed the normal seedlings, what we normally would get from the nursery. On the left side is Genesee, where we planted the same seedlings. However, there you don't see those differences as much. But Genesee was a site which had grown 5 years of alfalfa on it, and we plowed it under, and it was a very happy site, so it doesn't matter. So the more stressful site, on the stressful sites, it becomes more important to have a better seedling than on the good sites. Okay? Now, we went even further because we were told you can't nutrient load Aspen. Well, we were able to do it. You can see that we pretty much put another 30% or so of nutrients into the plant. So if we give the plant the nutrients in its pocket and we plant it, it doesn't have to compete with all the other plants, and you don't have to fertilize it as much. You probably still have to fertilize down the road, but it has it there, and nobody can take it away from that seedling. It's in the seedling. It's not in the plug. It's in the tissue of the seedling. Okay. So we did that with all kinds of the nutrients. So that works. No. Next point is the roots as propagules. We talked about seedlings. Can we use roots? Well, there were several studies we did now in the last few years where we transferred soil directly onto reclamation sites. And these were direct transfer. I can directly say this. We took cats, pushed the bush down, and then dug up the root system and threw it on the reclamation site. Really easy to say. It wasn't that easy. We did it on a 4-hectare plot. That gives you a bit of an idea. We pushed down the site, dug up the root systems, rode it, and then transferred it within, the whole process was done within 10 days. And we moved, I can't remember how many million, whatever. So we moved a whole bunch of soil and roots with that soil. And then we wanted to see, do those root fragments, those chunks of roots, because they get broken and shredded and whatever, can we use them actually as propagules for regrowing forests? So what we did is we collected roots in these sites, and we dug root pits. Poor grad students. They had to dig a lot of holes. Whoever works with me has to dig a lot of holes and roots and stuff. So, so they had to dig pits and find out where the roots are. Okay, where in the soil, because we had transferred 2 different depths, 20 centimeters and 40 centimeters, and we wanted to see where the roots are and from which depths would they sucker and make it to the surface. Okay, and how many of the roots will survive and so on. So first of all, root mortality is huge. We lose about 70 to 80% of the roots. They're never going to make it. That's reality. This is just what happens. And that was as good as we could do it. Okay? Because we didn't have it stockpiled for long. It was not rotting or anything. It was just transferred. And so we have a lot of mortality. There's quite a bit of damage, but there's also quite a few roots which survived or weren't physically damaged. And then you can see down at the bottom, you can see that the distribution of roots, we have them everywhere. At the bottom layer, we don't get too many roots, and that is probably how the trucks are unloading. But overall, the distribution of its roots is throughout the whole soil. I want to point out first the bottom graph, or the bottom table, sorry. That is the number of suckers we got from those root segments. So we got on average 3,500 if we transferred about 15 to 20 centimeters of forest floor. We got about 3,500 stems per hectare. If we did it at 40 centimeters at deeper depth, we got about 6,000 stems per hectare. This is very close, the bottom one is very close to the forestry standard of reclaiming, or sorry, of a natural forest stand after harvesting. And then in the second year we lost some through mortality, but they're still there, so they survive. Is it enough from how I see it? It's not, because when I want to see a forest, I want to have canopy closure as quickly as possible, so 6,000 stems per hectare is not enough, and they're clumpy too because they're suckers. So, but it does work. You can use that material, instead of wasting it in stockpiles, you could actually use that material and put it onto the reclamation site, and you would get a bonus. Let's call it that way, okay? So the suckers actually grow quite well, and they survived okay. So what we wanted to find out, though, is there such a thing as a sucker or a root fragment being too deep? So what happens to the 40 centimeter ones? Well, the 40 centimeter ones, here's the graph, so we had different sizes of roots, and we buried them at different depths. And what you see is that if we buried them at 40 centimeters, we didn't get any suckers. So if you reclaim your area and you have the salvaged soil, don't put them down at 40 centimeters, because whatever you bury at 40 centimeters is going to be down there and not going to make it. Those roots suckered, but the suckers grew 20 centimeters in the soil, and then it ran out of gas. Right? You have to remember, they have a chunk of root, and then they run out of reserves. There's nothing left. There's no water. There's no roots. Nothing. Okay? So they run out of that. So what you see is there on the bottom right is a non-emerged sucker. So you see lots of those ones popping up, but they don't make it to the surface. So the summary for that was, what we found is that we have a high mortality rate. The most suckers were produced from roots fragments in 3 to 20 centimeter depth, and the deeper you salvaged, so the more soil you brought with you, the better was actually the regeneration. And we think what it has to do with is that the root fragments actually are covered more with mineral soil, which holds the moisture properly, and if it's too shallow, it's too fluffy, so it dries out faster, and you get more mortality that way. That's what we think it is. But again, you don't have to waste your material. You can spread it out over a larger area if you have more than 20 centimeters. Now, we did a real neat study in the SAG-D where we looked at some of those temporary well sites and whether we can do forest floor protection and have aspen regeneration through that. So this is kind of what it looks like when we talk about the soil depths and the salvaging. You want to salvage and get most of the root system, and if you have suitable soil material, so not a BT horizon, which is just lumps of clay, but maybe you have a BM or some sort of a horizon, you can go deeper. Suitable soil material, you should be getting more of that instead of the unsuitable, right? So that's what we found from the first study. So we compared, can we protect the forest floor, and if we have to remove the forest floor layer, can we pilot on the side of the well site and then pull it back to like within a month? Okay, back onto the well site. So what happens currently is, by government regulation, the whole pad has to be. So if it's a slope pad, the whole pad has to be. The forest floor has to be removed, and then it's piled somewhere. And then they take the cut end and they fill it in, and then they have a flat surface. Okay, and that's when they put the rig on and do their drilling for months, and then they walk away again. And then they put the fill back onto, they recontour the land, and then they put that stuff back on top. So what we proposed is to remove just the top portion of the thing, pile it on the left side, and then leave the forest floor intact, put the fill on top of that. And then once they are done, remove that fill, recontour it, and then put the forest floor back onto the top part. And this is what it looks like. This on the right side is the protected forest floor, which was under the fill. It was removed and put back. On the left side is when we redistributed the forest floor. I don't think I need to show the numbers down there. I think you will believe me, it's a big difference, and we can do it. So the company will have to actually only reclaim half of the block or half of the well site. The other half is fine. Okay, so as you can see, the protected area, which was under the fill, and the control, which was just a cut area, and then you have the rollback on the bottom. The control actually had fewer suckers than our protected area, likely because we did some damage and some ruffling up of the surface and so on. And it actually, if it's not too much, it actually improves suckering. So it's doable. So what else does Aspen do? So we know it propagates really well. We can play around with it. We can use it a lot. It has other benefits. Litter, for example. On the left side, you have aspen litter of a 35-year-old aspen stand. On a reclamation site, on the right side is a 35-year-old pine stand. So what you see is a huge difference in organic material being deposited. And that's the thing when I talked about litter fall. Aspen is putting down litter every year, and it helps bringing plant carbon into the soil and starting the nutrient cycling. And I'm not a soil scientist. I work with a whole bunch of soil scientists together, and they look at the microbial activity and nutrient cycling and all that other stuff. I'm just providing them with the material so they can test these kind of things. And the idea, one of the reasons why the pine, and the spruce is even worse, has so little litter over the years is, first of all, the needles are much smaller, and they keep 5, 6, and in spruce 10, 12 years of the needles before they even drop the first needle. So in a spruce stand, it takes 12 years before you actually get litter on the ground. In aspen, it happens every year. Okay? So it's a big difference. How does it influence the soils? There's a bit of my soils colleagues' data. You can see up on top is soil carbon, and you see the development of aspen, pine, and spruce stands, how they differ in the amount of carbon in the soil, and they're pretty much the same picture with soil nitrogen. So aspen helps kickstarting the process because there's always carbon coming into the system right from the start. Okay? And that leads me to the next point is, well, the more aspen you have, the more litter you get, the more impact you have potentially on the site. So this is part of the same study. How much canopy you had was very important in the expression of how much carbon and how much nitrogen you had in the soil. So the closer the canopy, the higher the canopy closure, the higher the probability of having better nutritional and better carbon conditions in the soil. So the magic number was 30% canopy closure. I'm not sure whether there's a magic number, but that's the stats telling us. So I won't give too much credit to the stats. I think the earlier we can get canopy closure on these sites, the better. And if we get litter into these sites, which is easily decomposable, that's better for a site. So I'm playing right now in the all sands lots with planting high densities. We are planting 10,000 stems per hectare, aspen seedlings. Because reclamation sites are not forest sites. They're not forest management sites where you can't get away with planting 1,700 stems per hectare. If you want canopy closure and don't want the weeds, you've got to have high densities. I can't make them grow that fast that with 1,500 stems per hectare in 3 years you get canopy closure. I wish I could, but I can't. So that gives you an idea. There's a strip of aspen on the right side which is only about 3 meters wide. And it's planted at 40,000 stems per hectare just by accident. It was not, we didn't do that. It's not one of our research sites, but they wanted to have a buffer. That strip is only 3 meters wide. There's a wheat field on this side, like not a wheat for eating, like weeds. And then on the other side is one too. There's nothing growing underneath that aspen. It's like you put a ruler right next to those trees, and that litter fall keeps the competition down. And this is what I'm talking about when I talk about canopy closure and site capture. Do we need 40,000 trees? No, we don't. Okay? But do we need something like it? I think we do on many sites, especially in large sites. Because that is what we mostly see. And aspen, although it's very competitive and it's a weed, has really tough times with grasses. And people who know me, grasses and reclamation, if we can avoid it, avoid it. It's not the right thing to do if you want trees in forest land reclamation. They don't agree with each other in large quantities. You can have some grass, but if you have something like this, you will not grow a tree, or very poor trees. Okay? So, and to make that point, we grew aspen with and without trees, and you already see that one tree is a little bit wimpier growing with the grass, the other tree looks better, but where I'm getting at with this is not about, we know that if you grow plants with other plants, they don't grow well. We have done a million experiments like this. The question was, if that tree gets cut, let's say it gets burned, or we harvest it, or whatever it is, how is that root system going to behave? Are we getting regeneration? Remember, the root system is our bud bank, is the money in the bank. That's the resiliency. So we want to maintain our root system. Well, if you do that, there's a nice suckering here, and they did sucker in the grass, but you wouldn't know. The grass was actually cut off at the same time as the aspen was. Okay, the grass was as short as the aspen when it started suckering. And you have a tough time looking for those guys. And there's some of the results. On the top you have the emerged suckers. So these are the suckers which actually made it to above ground. And the black ones are the emerged ones, the gray ones are the non-emerged ones, and then on the bottom, Callum Gross, this was the grass we worked with, and then no grass, and you see the difference in the number of suckers coming up. And if you look at the bottom, you see why. Aspen occupies a different layer of roots below ground than the grass does. The grass sits on top, and all we know we can sod grass and we use it in our yards. We roll them up and unroll them back in our yards. That's the reason why we can do that. If we could do that with our aspen stands, that would be great. We would just roll up our aspen stand and roll it down onto a reclamation site. That would be neat. But we can't. But with grasses, you can do it. And what happens is you have that fine root system, that mat, on top of the aspen root system, and those poor little suckers, they got to grow through there. So it's actually a physical barrier for aspen suckers to make it through those thatch layers. So I'm at the end of my talk. So in summary, and I could keep on talking. I've done this for so many years. This is just a brief way of some of the things we have done over the years. I hope I convinced you that aspen is a good species. If you have some growing in your yard or on your land and so on, just cherish it. It's a fast growing and it's relatively stress tolerant. We know it grows in the prairies or at the edge of the prairies. Okay, we know it can do well on sites. It has fast and prolific root growth. And one of the reasons why we seed grasses is to stabilize sites. If we plant aspen to high densities, maybe we don't have to plant or seed grasses. Maybe we can seed actually some herbaceous species on top of that, and we actually create conditions which are more conducive to forest establishment, not to meadows with trees in it, which we do most of the time. Canopy development, I think I hammered that home for now. And aspen stands, I have this thing about nurse crops for other tolerant and intolerant trees. Aspen is really a neat species to work with. You can move an aspen stand to all kinds of different stand types. It doesn't mean that we have to plant aspen everywhere and we'll have aspen everywhere. It is the species, that's the reason why it's called it a foundation species, to set up our reclamation sites. For all what I care, if you have the nutrient cycling and so on going on the site, you could potentially nuke the aspen and plant whatever you want to plant on it, but the aspen it's kind of like a nurse crop. It had initiated all these natural functions of the site, and now you can move that site somewhere else if you want. That's management. That's a second pass. You do something else on top of it. Or you can open up these aspen stands if they were stay high density, which they generally don't. Aspen is not very tolerant of each other. So you will lose a lot of your 10,000 stems down the road, and you can underplant white spruce. So suddenly you get into mixed wood forest. Okay? So there's all kinds of stuff we can play with. You can bring in fir, balsam fir, for example. If you have the moister sites, you can bring in fir. So there are management we can do on reclamation sites down the road, or first we have to set them up, but down the road we can do thinnings. This is natural aspen suckering stands, and we thin them if the objective is growing big trees. And once the site is established and the system is working and the cycles are working, you can take out most of your trees and leave that 1,500 stems per hectare and you growing. Those aspen trees grew a centimeter in diameter every year when they were thinned. Okay? So you can do that, but you have to create first the conditions to actually have a forest.